interested in accelerated schemes for a class of numerical methods. In time discretization, so a class of numerical methods will be put into an abstract scheme where we can do the acceleration. So to present that scheme, let us consider V0, V1L, and so on, VL separable Banach spaces. The VL is embedded continuously in VL minus 1 and so on. V1 is embedded continuously and densely into V0. So these spaces measures the regularity of our equations. And we will use the norm, this what is written there. So when we write, we have a function and then we consider its norm, then the notation is written there, that is the I norm. Right, and we assume that, so let's see, we have already written, the basic equation is written there, so we have this equation in abstract form, so partial with respect to t, L Vt plus f, and with an initial condition V0, which is the V0, and that is in the finest, which is VL. So this is the equation we consider and want to approximate. We assume that the L operator is a bounded linear operator between these spaces from VL to VL minus 1 and so on. So we can think about differential operators here, so we will see some examples in a moment. The definition is written here, so a V-valued weakly continuous function is called a solution if this integral equation is satisfied, where the integral is understood in Bochner sense. Now basic examples, second order parabolic PDEs are covered, and also systems, parabolic systems of PDEs. So when we look for the solutions which are vector valued, and then the AI and A coefficients are correspondingly matrices, and what we consider then that the Aij is a scalar, so we don't consider very general parabolic system, but this system. So this is the second example, and then we split this operator L as it is written already there. So once again in this example, the AIA and AIR and AR, these are Q cross Q matrices. The solution is Q, a vector valued, and the main coefficients Aij is just a scalar. By the way, I forgot to mention that what I'm talking today can be found in an even more general setting in those papers. I hope I can also talk about Zonkwak approximations today, and that is in the third paper, which is to appear. Well, so we take P equals 2 in this setting, and for the solvability, this is the assumption plus regularity on the coefficients, and this assumption covers two cases. One when the main when the system is uniformly non-degenerate, and the second when it is degenerate, completely degenerate. That is then the left-hand side equals 0, this one. Completely degenerate, sorry, that, yes, completely degenerate, which means then the right-hand side equals 0, and therefore the left-hand side equals 0 as well, and that can be ensured if this here is the difference between the matrix and its transpose. So that means in this case that we have symmetric system. So this system is called symmetric first order symmetric hyperbolic system. So this example covers also the first order symmetric hyperbolic system. Right. Now, in order to describe the approximation scheme, so what is our aim is to approximate this equation, and we describe now a class of approximation systems. For that, we consider a right continuous function which is of bounded variation. This is h. In fact, a number of them, so d1. The assumption is that we want this period. We want that these functions be shift invariant with a shift or fixed shift. Let us take it 1. So take a shift. Let these be shift invariant. So we consider also theta, which is an operator, and theta r. So let me just fix that. We have the h, and the requirement is, and also hr, and the requirement is this shift invariance. And we have a bounded operator theta r, which are from these boldface wi to wi, boldface, in a bounded way, where the boldface I is defined as the weakly Kedlag vi valued functions on, so weakly Kedlag vi valued functions with the supremum norm. So weakly Kedlag means that weakly right continuous and with weak left limits, and the supremum norm is considered. And so bounded, these operators are bounded. Right, then the approximation scheme, let us fix that as well here, is that the dwt equals sum r1 d1 to d1 lr theta r wt plus fr dArt. I define this in a minute, and v naught equals v naught. Right, so this is the numerical scheme which still should be explained. So what is the ART here? We may make a time scale, so that ART equals the ht over tau times tau, where tau is our fixed parameter. and then just some examples. Right, so AR is defined there. Also, LR is just, we've split L into the sum of operators LR. Similarly, the free term is splitted, and from the LR, the same bondedness requirement is made, that is mapping from VL to VL minus 1 and so on as bonded linear operators. Okay, and then we consider this as in the integral form. The definition of the solution is in the integral form, just like before. So let us see some examples here. So the D1 case, so when D is 1, so we have only, we do not split the equation, and so the operators L into the sum of LR and the free term similarly, but just then consider this example, that take L1 then L, obviously, and the H1 is the integer part function, and then describes then the implicit scheme. Yes, because so then our a tau function is just the tau, let us go, I tau, it is I tau on the interval, right, yes, so maybe it is quicker if I make it, so this is just, here is tau, and then we have 0 until this, and then again and again, and so on. So this is just rescale the integer part function, and when we write then the equation, that is with this. So if we consider the dvt equals integral from 0 to t L dt plus f, or f, right, and then dA, and then we dAt with this one, then we can notice that this is just the implicit scheme embedded into continuous one. So, but at the grid, we consider also grid t tau, which is then with this parameter, the usual I tau. I is from 0, 1, 2, and so on, intersection the 0 capital T. Then on this grid, we get the implicit scheme. Now if we play with this operator theta, big theta, for example, we consider the case when the theta is defined as you can see here. This is the left limit of the function phi from these bold-face spaces, and the mixture of the left limit and the value can be taken with theta. When theta is 0, then that is just this small theta is 0, then this is just the identity, so we have the implicit scheme. When theta is 1/2, then that is called the Crank-Nicholson scheme, and then one can take any theta between 0 and 1. Right, when we split the operators into the sum of operators and also for the free terms, then by using the time scale functions, what we have seen before, then we have the splitting up method as well, and we can, using the theta operation, we can also combine splitting up with other method, right? So if you remember that if we consider these kind of functions for that is for AR, and so on. Let's say we have so in the case when we have only two, you remember we had just these two, and then periodic after that, and when periodic I mean the derivative is periodic, and then the other is like this, and these functions have the property, right, that they can be obtained by a shifting variant H rescaled. Right? So many variant can be done here, and now we formulate a general result then when the expansion is available. So the first assumption is that the original equation has to have a solution, and for each tau the approximation should have a solution, and moreover this is satisfied, must satisfy, so a stability property so-called, so there is no explosion in this norm when we run through all possible taus. In the examples I have seen, it is easy to ensure that these conditions are satisfied. Now the second is that this equation should be solvable for each k, and in another way to say it, that there exists this RK operator for this equation, which and in this term of RK operator we formulate that the solution is a mapping from the free term to in this way a bounded mapping between these norms, and that existence and uniqueness is satisfied. So this so in the term of this RK operator, the second condition means that we have an existence for this equation, and the other one, the next one here, says that in fact the uniqueness that is also satisfied. It is formulated like this. So whenever we take functions from V naught as free terms, and or sum of these functions, such that this equation is satisfied, then this must be our operator. Again, this condition can be ensured easily, and in that case, is that right? Oops, where have I gone? Right, so if these assumptions are satisfied, and we fix k non-negative integer, and the assumptions hold with an L, here is the L, yes, the L is the parameter for the regularity of the data. If L is greater than twice the k plus 1, k is the order of the expansion, then there exist functions yes, that is double phase V naught, which are independent of tau, such that for all tau we have the expansion on T, or on the grid, so for T on the grid. We don't have expansion everywhere, just on the grid. And moreover, that the remainder term is of order tau k plus 1. And then we already know that by a suitable mixture, I don't want to spend time on it, we can have the order of accuracy k plus 1. So this, in fact, the proof of this, and even in more general form, to cover more examples, can be found in the first paper I have written on the whiteboard. And let us now see an application to these results, or this general result, to ODEs. So we can apply for PDEs, parabolic, and also parabolic system of PDEs, but also one can apply this to ODEs. So consider an ordinary differential equation. This is here, where the right-hand side is split. The right-hand side we have a vector field B, and that is split into the sum of vector fields on RD. We assume that sufficiently smooth and bounded derivatives, these vector fields B1, Bm are, and then the splitting up method is investigated. So we want to solve this equation by solving the equations written here on each interval of length tau. So first on 0 tau, and you know just how splitting method is defined. That can be done also for nonlinear equations as well. So in particular for nonlinear ODEs. So this is what we do. Let PT and PRT denote the solution mapping. So the mapping, that means that which takes x, the initial value, into xt, the solution at time t, with that initial value. Oops, again. Right? Then we take a parameter tau and want to approximate PT, or the solution, by the product written here. So that means first we solve the first equation on an interval length s1 tau, then we take that take that as an initial value for the second equation, and solve and so on. Here these k1, k psi are any numbers from 1 to m. These are the labels of the equations, the 1 to m. So in some order we do that here also. The s1 tau and so on means that not necessarily we spend not necessarily tau time, but even more or less, even can be negative when we go backward in time. Right, so let us consider such a general scheme here, and that S tau is then when applied to the initial value, is considered to be the solution at time tau. And then we do this repeat and repeat and repeat, and then we get the solution or approximation of the solution at time I times tau when we repeat it I times. So obviously one should assume that the whole time spent for each of the equation is just 1. Yes, this is a requirement which we need here. This is the Kronecker delta. So this means that we add up all the proportion, how much an equation. So when we fix an r, yes, then it counts and add up the proportion of time we used one particular equation, and that proportion must be 1, so that we use it on a tau time. All right, so then we consider when we want to approximate at time t from the grid, then we t over tau times repeat this product, so this cycle, and then one knows, in fact, this is quite well known and used in the numerical methods of ODEs, that one can have such an estimate so that this method is of order 1, and so that this estimate is true under regularity condition. Right? Next, one knows also that if we have symmetric product here, you can imagine what does that mean, symmetric. We have already seen one. I don't want to give a general definition now. So one example is that strand product, which we have already seen. Then the estimate holds with tau square instead of tau. And then in general we can say that this product or method correspondingly is of order k if the error estimate holds for all x with tau k, in tau to the k instead of tau. And in the literature there are many methods of order k, and what we investigated or what we can get from the general scheme for this, that by using any of those methods, these type of methods, and mix them, then we get by this Richardson extrapolation method of any order. So let us formulate the result. So then the Wi means here the continuous functions over 0 capital T with values in Ci0, which means that the space of continuous function in X with such that their derivatives their derivatives in X up to order R are bounded and continuous. So first of all, the functions functions have compact support. This is why the 0 is there, and the derivatives up to order I are bounded, and so not compact support. Sorry, it's a little bit more general. That the supremum in time that vanishes towards infinity. So this is for what the C0 mean. And so this is the space which we will use to prove this theorem, which is formulated here, that assume that L is greater than or equal than 2k plus 2, and that the derivatives of the vector fields up to order L are bounded and continuous. Then for every tau we have this expansion where, as usual, the age are independent of the tau, and these are functions from the previous space V0. The remainder is also from V0, and such that in compact sets there exists a constant that the supremum over the compact set X and supremum over the grid, so that is maximum, in fact is estimated like this. And this result can be deduced from the previous one, from the general one, from the example of the parabolic or degenerate parabolic splitting, because we can consider the flow that for which is generated by the ODEs. So that, or in other words, we use that this equation ODE gives the characteristics of the first order PDE written here, and using the splitting up results for these equations, then we get this expansion result for the ODE. Right here we can see the references. So this is for parabolic, that is just for parabolic equation, and in fact what I have used here is this paper, but some parts, so you can find this then on the web. I don't spend more time, and now I go to a new topic, Von-Zakai approximation. This is about the rate of convergence of Von-Zakai approximations, and this is a paper together with Pablo Stinga, and will appear probably next year. I'm afraid not this year. Right, so the motivation for this first, for me, is the nonlinear filtering problems. I have written down here, so I repeat something which you already know quite well, I suppose. So we have the signal and observation model. For simplicity of presentation, I consider time independent, and even you see the observation, which is the y, is not included in the equation. As you have seen, it is possible. You have seen that in Professor Kurov's lectures. Right. So this is the scheme, and then the basic problem is to get the best estimate in mean square, and then we know that this is from classical results of Pardue and Kurov and Rozovsky, that if we have an initial conditional density, so first of all we know from school that the best estimate is the conditional expectation. The conditional expectation can be viewed by, or can be studied by studying the conditional density, and then if we have a conditional density in an Hn space, then the coefficients, derivative of the coefficients are bounded up to m plus 3, then the density can be obtained, that exists once, first of all, and can be obtained by normalizing the so-called unconditional density. This is the U, as you have seen in the lecture, and the unconditional density satisfies this equation, where the L is the adjoint operator of the one which is written here, the M is the adjoint of this one. This equation is called the Zakai equation. So then one can solve the filtering problem by one way is to solve the Zakai equation, and then what we get we normalize, and that gives you the density. There is also the nonlinear equation for the density directly. That is also a possibility, but it is more convenient to solve a linear one and then normalize it. Okay, so then the question now I am interested in is that suppose that the observation is just an approximation. The real observation, I would say, the Yn is just an approximation of the y. In fact, the y is a function of or process of bounded variation, so we can, a process of unbounded variation, yes, infinite variation, because that is just like the Wiener process. If we do give sign of change of measure, then just the Wiener process, so the parts are extremely irregular, so the observation, if it is considered in the oscilloscope like in continuous time, then cannot be in fact of infinite variation. So then a natural question is that if we, instead of the true or the or what is in the model, we have that, or instead of that we have an approximation for that which is of bounded variation and it converges, what can we say about the corresponding density, how they converge? And more importantly, we would like to know that if we have a rate of convergence for the approximation of the observation process, what rate of convergence can we say about the approximation of the density? Sorry?
So, the first question is that under general condition, is that condition or something we want to prove when Yn goes to I? Do we want to, maybe it's natural to show that Pn goes to P, not just the condition?
Sorry,
I'm confused at the word conditions. Under the general conditions, Pn goes to P.
Is there a robust such that, yeah, so maybe really this is confusing how I formulate it here. So one should know, or one knows from SDE theory, so the Wong-Zakai approximation results have been done maybe in the 50s, the first paper by Wong and Zakai, and those were for SDEs. And from those papers, and then there were many papers, one knows that if we replace the driving process, let's say driving Wiener process, by a process of bounded variation, and then we take it to the limit when this bounded variation sequence of bounded variation processes converge to the Wiener process, then we get at the limit that it satisfies not the original equation but the equation in the Stratonovich form. It is easy to explain why this should be the case, but I don't have time now for that. But anyway, with this experience, one can already expect that at the limit, if there is a limit in this infinite dimensional case, then the limit is not satisfying the same equation, but something which corresponds to the Stratonovich form. And when Stratonovich equation in the infinite dimensionals, and when I started with this, Professor Kulov suggested me to consider this question, then it wasn't known at all what would correspond to this one, and even in some applications area in physics, then as a magical thing it was noticed that in these approximations something strange happens, that an extra terms appear, and in fact the limit equation, which now we understand is completely analogous to the Stratonovich version of the SPD, there in the limit equation a second order term appears, so the limit equation is different. So maybe this is why I formulated like this in such a confusing way, but that we will see then what is. So therefore, what I call, what we already expect now, or we know already now what is the limit equation must be. Some people call it that first we write the Zakai equation into a robust form, which means that formally here we take the Stratonovich differential. This is just formally written here. I don't want to define in this setting what does that mean, Stratonovich differential, just accept that here this means that we consider the usual E2 differential plus, and here is the second order differential operator appearing, and you can notice that in this case this corresponds to the Stratonovich form of but that time it wasn't clear in which form that will appear in this easy form. Right, we rewrite this in this form, but then we should compensate. So L bar here is L minus, we take this out. Yes, because when we write it like this, then the extra term is by definition appears, so here we subtract it, and this is called the robust form of the Zakai equation. And now into this robust form we substitute in place of the y the approximations, and in that case the limit is expected what really should be, because that extra term is right, is just vanishing. Okay, so let us see the result for SPDEs. So our aim is to show that if the signal process is approximated with in some order, then the density function, by solving the Zakai equation and normalizing and getting in this way an approximation, that approximation is converging with nearly the same rate to the true density function. In order to show that, we just consider the general case for SPDEs. So we consider an SPDE in this form, and replace, so here for simplicity we take the Wiener process. In application that's enough for filtering, because in fact up to a change of measure we have a Wiener process, as we know, but we can take here any continuous martingales and also time independence, but in the presentation the L is just the second order operator, M is a first order operator, and time independent, and here is the approximation. So the W is approximated by a sequence of processes, continuous processes of bounded variation, and we consider here so-called spatial approximations, because, and I will define what do I mean under that, because we know that in general, and that I should have told again to give a complete answer to your question, why, that under which condition, in fact I haven't answered that properly. So von Zakai papers were in one-dimensional case first, and in one-dimensional, when the driving noise is one-dimensional, then there is the convergence easily proven or proved. But in the multi-dimensional case, it turns out that there is no convergence in general, because of the interaction between the noises, unless one has an assumption that the vector fields in front of the noises, their Lie brackets vanish. Then one can show that there is the convergence, but that is a very strong assumption, and therefore the investigation was how can we assure without such a condition on the sigma fields the convergence of the Von-Zakai approximations, and then it turned out that the so-called Levy area processes play an important role in order to get the convergence. So let us then see what is this about. So for the original, for the Wiener process, this is called the Levy area process here, or one half of this. Then let us consider also this, which is the Levy area process for the approximation. And then we call a good approximation of order kappa, such an approximation Wn to W, if we have for this positive kappa that for almost every gamma, almost surely first we have the approximation uniformly in time of order n to the minus gamma. Yes, so big O n to the minus gamma is the rate of convergence, almost surely. So this is the first. But that we know from finite dimensional results that it is not enough to ensure the convergence. So the Levy area processes, so here we have I and J. Obviously when I equals J, then this is zero, no assumption. So the Levy area processes should converge with the same rate, and that this process here, the S process, should have finite variation controlled, and my assumption is that must be, or our assumption, must be little o ln. So slowly it can go towards infinity, but very, very slowly. And here I would like to turn your attention to this notation is for the total variation of the process over the interval 0 capital T. So these are the assumptions on the approximation. So we say that good approximation for the Wiener process of order almost kappa. Some examples. So the polygonal approximation, which is written here, then smoothing, like written here. These are the basic examples, and these approximations are good approximations with order 1/2. One can show that, but there are many other examples as well. Now the assumptions on the SPDs are formulated. So let lambda be a positive number, that is for the ellipticity condition. As you should notice that when the equation is written in the Stratonovich form, then the stochastic parabolicity condition is just the usual ellipticity condition for the SPD. If I write it back, then if that is not in the parabolic, not in the Ito form, not in the Stratonovich form, then obviously we should have the stochastic parabolicity as we had known. So that is also an M fixed, and you have seen already these conditions. Up to M we require the derivatives exist, are functions bounded by K. The initial condition from here, as usual, the F, the free term at the drift is from here, but this is a bit unusual for the a non-degenerate case. Lambda is positive here, so here something more required than usual. Okay, so these are the requirements, and then the main result here is that if Wn is a good approximation of order almost kappa, and the previous assumptions from 1 to 3 are satisfied with m equal or greater than or equal to L plus 4, then in the L norm, this is the L2 norm, uniformly in time we have that the rate of conversion is almost the same, so for every alpha, so again just we can say that it is of order almost kappa. If here we have the order almost kappa, then the approximation rate is also almost kappa in these two norms. Now just some remarks concerning the history of this. So in the 80s there were some papers showing the convergence of von-Sakai approximations, among them mine, showing the von-Sakai approximations but without rate of convergence. Oops, is that?
That's fair.
Yeah. And then I think that the first, what I have no, sorry. Concerning rate of convergence, the first what I have noticed in the literature, but I might be mistaken, is a paper by Brezhnev and Flandoli, and there used just the polygonal approximation and different method point-wise using the method of characteristics, and then they got that it is 1/4 the rate, but remember the polygonal approximation has rate 1/2, so this is not optimal. Then we together with Anton Schmatkov proved proved that for the general scheme, but we also got only half of that what is expected. So in fact if we apply this to the polygonal approximation case, we also get only alpha less than 1/4. So we did more general result, but the rate of convergence in fact is about the same, and the reason was somehow we were not able to do separately from the rate of convergence to prove first that the approximating sequence of solutions is bounded in the norm or nearly bounded or something like this. We got that only after that first we could prove that there is the convergence and the rate, and from here already follows obviously the weaker thing that the approximating sequence is bounded almost surely, but somehow the right way in numerical analysis is first to prove boundedness for the approximating sequence, and then using that proving the rate of convergence. And so we together with Pablo managed to do that, and now I give the hint of the proof here. So here first estimate the growth of UN. UN is the approximating sequence, and for this we prove the following proposition, that if we have that under the conditions of the theorem, which is the main theorem formulated here, there is such that is stupid which I wrote here, sorry. The expectation, please omit here the expectation. I got used to write expectation so many times here at the whiteboard, so I put that I'm afraid when I corrected or put that here. So without the expectation, it says that the growth is, and in fact here until capital T, so I should correct this here also until capital T, we have that the growth is of order n to epsilon for any small epsilon. That means almost bounded, and that will be good enough for us, that for any epsilon we have this almost boundedness in this norm. So one needs to have a higher norm, the boundedness, than one proves the rate of convergence. So the rate of convergence is proved in the norm L, but to do that one needs the growth in a stronger norm. Now this one is not so hard to get, so we apply Ito's formula in L plus 3 for the square of the norm in L plus 3. So for this quantity then, after long or not so terrible computations, we can show that this is estimated like it is written here, just to go towards Grunwald inequality, or a version of Grunwald inequality. In this case here, the Qn is a continuous process of bounded variation, in fact increasing continuous process. MNT is a local martingale, but this kind of estimate for the bracket or the process, or the Dubmeyer process, we have this kind of estimate with this Z here, and G is the free term in the diffusion part. And moreover, we know about Qn that it doesn't grow quickly, so small o ln n. So once we have this, then from here a version of Grunwald lemma gives the result. The proposition proves the proposition. So this is.
So is lambda elliptic constant?
Here, yes, here the lambda is really right. I can take maybe lambda half. Let me go back. Maybe one should have how was the ellipticity condition was written with lambda, then you notice the mistake. It should be lambda half, in fact. So we always lose a little bit from that. So that is in fact lambda half, but doesn't matter. The important thing that we have there any fixed positive number. And here you remember, so we have the Mn, then the Rn is a process, a continuous process, and we can get this estimate, but only first one can get it by stopping. So tau n is a sequence of stopping time. So oops, the L plus R went up to this is the norm. Sorry. Well, in fact here the UN squared and the norm L in L plus R space, which is written here, and one should define a sequence of stopping times where we stop accordingly to the sequence, and with a power at n which is less than the kappa, which is the rate of convergence we want to get. So if it turns out from the calculations that in order to get this Rn under control, that is a big O and epsilon, then first one should in fact stop it. So this is the stop process accordingly, and if we get this stop, then we can also use, okay, let us first accept that this is true with this sequence of stopping times, and then something about the calculations. So going back here, I mentioned that certain calculations should be done, and these calculations are based on. I was here. So this ignore this here. Instead of the L is just an absolute value, so that this quadratic form absolute value is estimate. No, that's in fact correct. Sorry, I am not talking well here. This L denotes the inner product in HL, so in WL space. So the L stands here for that inner product. So that means when we consider the MV, we should take still L more derivatives, also L derivatives up to order L, and for V as well, and then consider the L2 product. So you understand what I mean, inner product in the WL space. It's absolute value, so the only thing is that the absolute value is missing, is estimated by this. But this is not a hard thing, in fact. So when L equals 0 is just a kind of trivial thing. So just MVV, as this is a first order operator. So then this is just the same as the V and then the adjoint in 0. So it means if we take now the M plus N star VV and take half of it, then this is just the same, and then here this is a 0 order operator. Yes, because the first order the adjoint of a derivation is minus, and then there are derivatives on the coefficient. So anyway, this is a first order, so it is not a big surprise. Not a big surprise that we can have then such an estimate. So the L here is not L plus 1, which would be the first term, but L. Okay. Do I have still 5 minutes? 5 minutes, thank you. And right, there's another one which is needed in these calculations is a similar cancellation property. So L is a second order operator, M is a first order. So then the inner product in L is considered, but in a symmetric way. And then we can estimate it by the L plus 1 norm, so this quadratic form. And then even in the degenerate, when the lambda equals 0, even more sophisticated or more of this kind of relations or estimates are needed. Okay, but then by these two we arrive to the kind of estimate which or inequality which we have seen, and then a Grunwald inequality version gives the proof of the proposition. So here is that formulated as a lemma. Once we have these continuous processes where Mn is a martingale, it has this kind of estimate. The Qn is a continuous process which is growing as n to the gamma, and what else? And the Q, which is the increasing process, is slowly increasing. There, and also here the K also slowly growing. This is when gamma is positive, then this lemma is about the growth. if gamma is negative, then this is about how quickly it goes to zero. Well, so if we have this, and then we have almost surely that that it is for every kappa, this kappa is unfortunate because that is fixed, but for any kappa which is greater than gamma, then the solution uniformly is of big order n to the gamma. So by this lemma we can control the rate of convergence. So this is just a version of Gyongy lemma, maybe it is useful, which is about the rate of convergence. And another lemma, which is also this one is a simple technical thing, but very useful, that if we want to prove about a sequence of Kedlock processes, let's say in more general, that it is the sequence, I lost the n, again a mistake here instead of the t, the n must be, and the t in parentheses, then if we want to see that it is its rate of convergence to zero is big order n to the gamma, then in fact it is enough to prove that the stop process has that rate, and we can stop with a slower than n to the delta with any delta, or with any fixed delta which is greater than gamma, we stop it. And so with this sequence of tau n, if we can prove this, then then it follows that we have the rate of convergence. So this is a useful technical tool which we use, and then we prove the first step, but I think I don't have more time, yes, for the second step. So maybe I should leave it. Do I still have?
It's a minute.
2 minutes. Then all right, that might be enough for the second step. Oops, if I can handle well the. So the second step is the rate of convergence now, how to prove the rate of convergence. So the strategy is that we find suitable processes Rn such that due to the growth estimate in the first step, we can control its growth in this way, that it is almost, or a rate of convergence to zero, that it is almost over the kappa, and then if we in this L norm, so then we can take it out. So these kind of processes doesn't matter if we add, subtract, multiply by constant n. So we can take it out from the u minus un, and prove that for Vn has then that required rate of convergence, and we choose Rn such that the Vn satisfies the suitable equations from where we can get the rate, as we have seen in previous lectures, because here the Gn, if we do that well, the Gn and the H and rho, these processes have rate of convergence towards zero over the almost gamma, and we need that this, which is a process here, sequence of processes of bounded variation, doesn't go fast, so slowly, so small o ln n. So if we can show that this one is satisfying such an SPDE with, once again, with a sequence of Bn, which is of bounded variation, and the variation over 0 capital T is big order ln n, and once again, let's see, that is probably on the next slide. Yes, so here we are. that the initial condition goes to zero as we wish for every, so almost with the rate of kappa. Then in this sense, these senses, the free terms converge. And here for the driving B, we have the slow rate of convergence. Then we get that under the assumptions with ML maximum 1, and assume that the previous, this is the assumption 4, and that the ellipticity condition, then we get for the Vn that it is of the rate of convergence towards zero in the L norm is almost kappa, also for the integral norm in L plus 1. And then from here the theorem follows, because the Vn differs from the error with something with Rn, which is controlled, which has the same growth or the same rate of convergence which we want to prove. So this is the end. Sorry, I overstepped the time.